You learned three properties of determinants in the first part of this lesson, which simplify evaluation by obtaining the maximum number of zeros in a row or a column. Now, let us learn some more properties of determinants. The fourth property says that if all the elements of a row or a column of a square matrix are multiplied by a number, k, then the value of the determinant of the matrix obtained is k times the determinant of the given matrix. Let A be a 3 by 3 square matrix as shown. On expanding along the first row, determinant A is equal to A1 times of B2 C3 minus B3 C2 minus A2 times of B1 C3 minus B3 C1 plus A3 times of B1 C2 minus B2 C1. Now, let B be the matrix obtained by multiplying each element of the first row by a constant k. Expanding B along the first row, we get k into A1 times of B2 C3 minus B3 C2 minus k into A2 times of B1 C3 minus B3 C1 plus k into A3 times of B1 C2 minus B2 C1. Taking k common, we have determinant of matrix B is equal to k times determinant of matrix A. This verifies the property. By this property, we can take out any common factor from any one row or any one column of a given determinant. Two results can be deduced from this property. The first is that if the elements of a row or a column of a square matrix are k times the elements of another row or column, that is, if two rows or columns of a determinant are proportional, then the value of its determinant is 0. Let's verify this result with an example. Consider determinant A, such that its second and third rows are proportional. Here, each element of the third row is 2 times the corresponding elements of the second row. Now, from property 4, on taking 2 common, determinant A can be written as 2 times the determinant whose second and third rows are identical. And from property 3, we know that if 2 rows or columns of a square matrix are identical, then the value of the determinant is equal to 0. Hence, the determinant of A is equal to 0. This verifies the result. The next result is that if M and N are 2 square matrices such that M is equal to K into N, where K is a real number, then the determinant of M is equal to K raised to the power of N into the determinant of N, where N is the order of matrices M and N. Let us apply this result to a matrix M. It can be written as 2 matrix N, where N is a matrix with the entries 5, 1 in the first row and 3, 4 in the second row. On evaluating, determinant M is equal to 68. And on evaluating determinant of N, we get 17. Observe that determinant m is equal to 2 square into determinant n. This verifies the result. Moving on to property 5. It says, if the elements of a row or a column of the determinant of a matrix are expressed as the sum of two or more terms, then the determinant can be expressed as the sum of two or more determinants. Suppose the elements in the first column of a determinant are expressed as the sum of two terms. Let's show the determinant can be expressed as the sum of two determinants. Consider the left-hand side. Expanding the determinant along the first column, we get A1 plus L1 times of B2C3 minus B3C2 minus of A2 plus L2 times B1C3 minus B3C1 plus A3 plus L3 times B1C2 minus B2C1. On simplifying, it can be written as shown here. Observe that the first three terms of the expansion of the first determinant along the first column and the last three terms are the expansion of the second determinant along the first column. This is the required right-hand side. Note that similar results can be obtained by considering the other rows and columns. For example, consider the 2 by 2 matrix shown here. Its determinant is equal to AD minus BC. Now, let's find the determinant by writing it as the sum of two determinants. Using property 4, take -1 common from the second row of the first determinant. Now, the first determinant has two identical rows. So its value is 0, and the value of the second determinant is equal to AD minus CB. Hence, the value of the determinant is equal to AD minus BC. This shows that the value of the determinant is the same as the value of the determinant when it is expressed as the sum of the two determinants. Moving on to the last property. It says, if the elements of a row or column of a square matrix are added with k times the corresponding elements of another row or column, then the value of the determinant of the given matrix does not change. That is, the value of a determinant remains unchanged if we apply the operation Ri goes to Ri plus k times Rj, or Ci goes to Ci plus k times Cj. For example, if we apply the operation C1 goes to C1 plus k into C2 to matrix A, the resultant determinant of matrix B has the same value as that of determinant A. Let's verify it by expanding the resultant determinant B. Take a look at determinant B. Observe that the elements in the first column are the sum of two terms. By property 5, we know that if the elements of a row or a column of a determinant are expressed as the sum of two or more terms, then it can be expressed as the sum of two or more determinants. Hence, determinant B can be expressed as the sum of two determinants. In the second determinant, each element of the first column is multiplied by k. By property 4, we can take k outside the determinant. which will not change its value. Now, we have determinant A plus K times a determinant whose first and second columns are identical. By property 3, we know that if two rows or columns of a determinant are identical, then its value is equal to 0. Thus, we have determinant B is equal to determinant A, and hence the result. Note that similar results can be obtained by considering the other rows and columns. Let us consider an example now. Without using property 6, the value of delta on evaluating comes to 0. Let us now apply property 6 to this determinant and verify that in both the cases, the result is the same. Applying column operation C1 goes to C1 minus 6 times C3. We get the determinant with its first two columns having the same entries. Now, by property 3, if two rows or columns of a determinant are identical, then its value is 0. Observe that either way, the result is the same. But with the help of properties of determinants, it can be simplified more easily.